Today's video, we're going to be studying chemical kinetics, and here we have the outline of what we'll be discussing. Factors affecting reaction rates, differential rate law, and integrated rate law. Now, chemical kinetics is the study of the rate of reaction. In other words, is the study of the speed at which reactions take place. Now, some reactions take place very fast. Some reactions are very fast, almost instantaneous, and some reactions are very slow. They take a long while to be completed, and there are various factors that affect reaction rate. Now, when we talk about reaction rates, given a reaction where we have the reactant A plus B forming the product C, the reaction rates can be defined in two terms. The reaction rates can be defined as the rate at which the products, or rather the rate at which the reactants are converted to products, or the rate at which the products are formed. Okay, so it could be defined in terms of reactant disappearance, or product formation. Now, of course, this is with respect to time. Okay, this is with respect to time. Now, for the reactant disappearance, the final amount of reactants, now this could be concentration, it could be volume, or any other quantity used to determine the amount of reactants. The final amount of reactants, let's say VF, would be less than the initial amount of reactant. So this means that the change in the amount would be negative, so it would be less than 0. Now, to account for this negative sign, when using reaction rates in terms of reactant disappearance, we include a negative sign divided by the change in time, and this is also divided by the change in time. Now, as I stated earlier, different factors affect the rate of reaction. Some factors help to speed up the reaction, some factors slow down the reaction as well. But for this video, we'll be looking at factors that increase the rate of reaction. The first factor we'll be considering is temperature. Now, temperature is, as we know, the degree of hotness or coldness of a body. But more than this, temperature is a measure of the average kinetic energy. So it's the measure of the average kinetic energy of the particles or the molecules that make up a substance. So this means that an increase in temperature would lead to an increase in kinetic energy. Now, just before we continue, in chemical kinetics, we have the theory of collision, or the collision theory. Now, the collision theory simply states that for substances to react, they have to collide with a certain amount of energy. So if we have substance A and substance B, for these two substances to react to produce substance C, A and B would have to collide, and they would have to collide with a certain amount of energy, okay, in order for reaction to take place. And they would also have to collide with the right orientation. So energy and the right orientation. Now, how does temperature influence this? Now, with the increase in kinetic energy due to rise in temperature, the molecules A and B would have a higher kinetic energy, and so their collision would most likely result into a reaction. Such a collision that results in a reaction is termed an effective collision. So an increase in temperature leads to more effective collision, increases the frequency of collision, and hence more effective collisions are likely to take place. Next factor would be considering is concentration, and would be considering the concentration of the reactants. Now, take for instance, you have a box, okay, and in this box you have a group of people that are blindfolded. Okay, so you have this group of people that are blindfolded, and you ask them to move randomly within this box. Okay, if you have two people, the probability of these two people colliding would be quite low. Okay, but if you have in this small box 100 people, the rate at which they would collide would be very high, because the space is not so much, and so people are colliding because they are moving about. This is the way concentration affects reaction. Okay, so when you increase the concentration of reactants, it will generally lead to an increase in the frequency of collision, and this increase would mean that there would be more effective collisions and more reactions would likely take place. Okay, so this is how concentration affects reaction rate. When we look further into the rate laws, would see how it plays out properly. The next factor would be considering is surface area. Okay, now in chemistry, when we have a small piece of substance like this, and we have a big chunk of substance like this, this small piece is said to have a large surface area as compared to this large chunk. Now, how does surface area affect the rate of chemical reaction? Now, let's take for instance that this small piece is a piece of zinc, and this is a larger piece of zinc. Now, if we want to react, take for example zinc plus HCl. Okay, so this is aqueous and then this is solid. If we have smaller pieces of zinc, they would react faster compared to if we had big chunks of zinc. Okay, so if we have, this is a test tube with small pieces of zinc metal, this would react faster than if we had just the reaction taking place with a large piece of zinc. Now, surface area affects the rate of reaction, and that is the reason why it's easier to light or to start a fire with smaller pieces of wood as compared to a big log of wood. You can start a fire easily, as we can see in this picture. You can start a fire easily with small pieces of wood shavings as compared to a big chunk of wood. And surface area affecting reaction rate is also the reason why if you have a tuber of yam, you won't just cook the whole tuber of yam. You would have to slice it, as we have here. You'd have to slice the yam in order to ensure that it boils completely. If you have this big chunk and you just boil the entire tuber of yam, what you would have is a peripheral cooking. So only the outer surface of the yam would be cooked, but the inner surface won't be cooked. And this also plays out in chemistry when you have a big chunk of a substance reacting as compared to very small fine particles, finely divided as it is called. The next factor affecting reaction rates that we'll be considering is catalyst. Now, what is a catalyst? A catalyst is a substance that decreases the activation energy of a reaction. So in a reaction, we have what we call the activation energy. Now, the activation energy is the minimum amount of energy required for a reaction to proceed. So for a reaction to proceed, you need a minimum input of energy, and then the reaction kicks off from there. It can also be defined as the minimum energy with which reacting particles must collide in order for reaction to take place. Now remember, when we spoke about the collision theory, we said that the molecules reacting have to collide with a certain amount of energy and in a particular orientation. Okay, now activation energy can be defined as this energy, the amount of energy, the minimum amount of energy with which the particles must collide in order for reaction to take place. Now, what a catalyst does is that, take for instance, the minimum amount of energy is 10 joules. What a catalyst does is that it decreases this energy to, say, 5 joules. Now, it means that other collisions that were taking place, so take for instance, you had A and B, or A1 and B1 colliding with 6 joules. So without the catalyst, A1 and B1 were colliding with 6 joules, but because the activation energy was 10 joules, their collision could not result in a reaction. Okay, now when you add the catalyst has decreased the activation energy to 5 joules. So what happens now is that A1 and B1 that were once colliding and could not result in a reaction can now collide with just that amount, 6 joules, and it results in a reaction. So it means that more reactions would be able to take place. Looking at the graph of energy against the progress of the reaction progress, we can see that here we have the reactants. So the reactants are here at a low energy, okay, and they have to attain certain amount activation energy in order to get to the product. Okay, so this is the activation energy. Now at this place we have the activation complex. So the reactants have to collide with a certain amount of energy in order to get here. So A and B, or A1 and B1 that once collided, they probably got to this amount of energy, but they could not cross over to the activation energy level. Now with the catalyst, what happens is that the catalyst probably decreases it to just about here. So the catalyst provides a new pathway. It provides a new pathway for the reaction. So now this is the activation energy. Okay, this is the activation energy. Now you can see that A1 and B1 that couldn't react before can now react and cross over to the product side. This is how a catalyst affects the rate of a reaction, and the catalyst itself is not consumed during the reaction process. Okay, now for this video, these are the 4 factors we'll be considering. Now, according to our outline, the next topic of consideration, or the next subtopic of consideration, is differential rate law. Now, the differential rate law relates the concentration of the reactants to the rate of the reaction. Okay, so to the reaction rate. What the rate law does is that it tells us how the concentration of reactants affects the reaction rate. Okay, now we have 0 other reactions, as we'd see for this video: 0 other reaction, first order reaction, and second order reaction. And we'll take a look at each of these individually. Now take for instance we have the reactants A and B reacting to give us C in a zero order reaction. Now in a zero order reaction we have the reaction rate R equal to the rate constant. Now the rate constant remains the same. The rate constant is unaffected by concentration. It's only affected by surface area and temperature, but won't be considering that in this video. The rate constant, as the name implies, is constant, and in a zero order reaction the rate of the reaction is equal to the rate constant. Now why is this so? The general form for the rate law, for the differential rate law, is R is equal to K A to the power of M B to the power of N, and so on, depending on the reactants that affect the reaction. Now considering this reaction, which we have assumed to be a zero order reaction, to be a zero order reaction means that the exponent here would have is 0. Okay, now what does that mean? It means that the concentration of A as well as the concentration of B has no impact. It has zero impact, as the name implies. It has zero impact on the rate of reaction. So whether you increase the concentration of A to infinity, increase the concentration of B to infinity, the reaction would take place at the same rate. Okay, so this reaction is unaffected by concentration. That's simply what it means. So we have the concentration of A raised to the power of 0 and the concentration of B raised to the power of 0. Now take note of the fact that the differential rate law relates the rate of the reaction to the concentration of the reactant. Do not make the mistake of including the concentration of the product. Okay, it's just the reactants A and B, and any number raised to the power of 0 is 1. Okay, so we'd have this being just 1, so R equals K. Taking a look at the general form for the differential rate law. Now it's a differential rate law because it makes use of differential or differentials. Now from our calculus knowledge, we know that differentials or derivatives has to do with rate of change. Okay, and here we are dealing with the rate of change. So the rate of change of, or rather the rate of the reaction, which of course is a rate, okay, with respect to time. The next order of reaction would be considering is the first order reaction. Now, taking a look at the general form for the rate law, K, A, M, B, N, and so on, according to the number of reactants that we have. Take for instance, we have a reaction A plus B giving us C. Okay, now a first order reaction is a reaction in which the order is 1. Now what does this mean? In a first order reaction, we could have 2 reactants. Okay, in the first order reaction we could have 2 reactants. Then you say, why do we have 2 reactants but we only have the reaction being affected by the concentration of 1 reactant? We'll take a look at that when dealing with reaction mechanism. But for now, take for instance our rate is equal to the rate constant, and for this particular reaction it's affected by, say, the concentration of A. However, the rate order with respect to B is 0. Okay, so taking a look at this reaction, this is a first order reaction, although we have 2 reactants. So how we interpret this is that the rate, okay, the rate of the reaction is first order with respect to A and zero order with respect to B. However, the overall order of the reaction is 1 plus 0, which is equal to 1. So the overall order of the reaction is 1. Okay, now what does this mean? This means that if we increase the concentration, or if we double the concentration of A, the rate of the reaction would be doubled as well. Okay, double the concentration of A, rate would be doubled. If you half the concentration of A, so times 1 over 2, the rate would be halved. Okay, if you triple the concentration of A, the rate would be tripled as well. This is simply what it means because it's a first order reaction. Of course, any number raised to the power of 0 is 1. We could simply write the rate law as R equals K concentration of A. Okay, this is the differential rate law for a first order reaction. The next order of reaction we'll be considering is the second order reaction. Second order reaction. Now, in the second order reaction, we could have something like this: A plus B reacting to give us C. Now, the second order reaction could be R equals K concentration of A and concentration of B, or we could have R equals K concentration of A square, or we could also have R equals K concentration of B square. This is a second order reaction. Now notice for the first equation that we have here, the order of the reaction with respect to A is 1, and the order of the reaction with respect to B is also 1. However, the overall order of the reaction is equal to 1 plus 1 and is equal to 2, making it a second order reaction. Here, however, we can see that the rate is only affected by the concentration of A, and the rate of the reaction with respect to A is a second order. So we can have something like this: A square, and with respect to B it's 0. Okay, and here we can also have R. The reaction is only affected by the concentration of B in a second order, so B square, and then A here is raised to the power of 0. Okay, now what happens in a second order reaction? In a second order reaction, taking a look at what we have here, just considering K equals, or rather R equals K A square. Notice that if you increase the concentration of A, so take for instance you double the concentration of A. Now, because this is squared, it means that the rate of the reaction would be quadrupled, okay, multiplied by 4. If you triple the concentration of A, so times 3, the rate of the reaction would be times 9 because it is squared. So we can see that the rate of the reaction for a second order reaction, the concentration of the reactants greatly affects the reaction rate, as we can see here. Okay, so the rate order, or the rate law for a second order reaction, K equals A square, or when it depends on two reactants, K equals A and B. Okay, this is how a second order reaction looks like. Now, taking a look at the general form for the rate law, which is R equals K AM and Bn and so on. How exactly do we find M and N, the order of the reaction? Now, generally or sometimes we could have a reaction, say 2A plus B gives N, or rather gives C. Now, it's important for us to take note of the fact that the value for M is not necessarily 2. Simply because we have 2 moles of A doesn't mean that the reaction rate with respect to A would be 2. However, it could be 2, but it's only a coincidence, okay? The mole of the reactant does not necessitate that the reaction order with respect to that reactant would be the mole, okay? So M is not necessarily 2 and N is not necessarily 1. The order of the reaction is gotten experimentally, and in this video we'll be taking a look at an example in which we can get the order of the reactants. Right, now we can see in this table that we have 3 trials of an experiment A plus B reacting to give us C. Okay, we have 3 trials of the experiment: trial 1, trial 2 and trial 3. Now, for each of these trials, the initial concentration of A was gotten to be 0.1 moles per liter, 0.1 again, and 0.15. Here we have 0.1, 0.15 and 0.1 again, and here we can see that the rate of the reaction was calculated. Okay, take note of the negative sign that we have here for the rate of the reaction. Now, why is this so? As the reaction progresses, as I stated earlier, the amount or the concentration of A decreases with time. So if we had an initial amount of, say, 5 moles per liter, or let's just say 5 moles, okay, and then we have a final amount of, say, 3 moles. Now, change is calculated as final minus initial over time. So this happened in 2 seconds. Okay, now the final would be 3 minus 5 divided by 2, which is equal to negative 2 divided by 2. So it means that the rate would be negative 1 moles per second. However, the negative that we have here helps to deal with having to have a negative rate. So this negative multiplied by this negative would give us a positive 1 mole per second. Okay, and conventionally rate is always positive, just as time is always positive as well. Okay, now how exactly do we solve a problem like this? So the general rate law would be R equals K, concentration of A raised to the power of M, and concentration of B raised to the power of N. Okay, these are the 2 reactants that we have. Now, merely looking at the reaction that we have here, we can't say that because the mole of A that we have is 1, then M should be 1, and because B has 1 mole, then N should be 1. It doesn't work that way. Okay, now let's take a look at how to solve a problem like this. Now, in solving problems like this, consider 2 reactions. Okay, so consider 2 reactions, say X and Y. in which the concentration of A is the same for X and Y, but the concentration of B changes. Consider another set of reaction U and V in which the concentration of A changes and the concentration of B remains constant. Now we'll start off with A. Okay, now taking a look at this table, we can see that in the second and third reaction, the concentration of A changes. However, the concentration of B also changes in these two reactions, so we won't be making use of 2 and 3. Now, taking a look at 1 and 3 for A, we can see that the concentration of A changes while the concentration of B remains constant. Now, we'd be making use of concentration of reaction 2 and 3. Okay, so for R2, or rather would be making use of 1 and 3. Okay, so R1 would be equal to K AM BN, and R3 would also be equal to K AM and BN. Okay, so the concentration of A, as we can see, is 1 and 1.5. Okay, so 1, 1.5, 0.15, 0.1 and 0.15, and for B it remains constant as 0.1. Okay, so for B, this is for A, and for B it remains constant at 0.1. Now, imputing this into each of these equations, taking the rate, okay, so for the rate we had 0.03 and 0.067. Okay, so the rate here for R1 is 0.003. Okay, R1, as we can see here, and for R3 it's 0.067. so R3 equals 0.00675. Now let's work with these two values. Okay, now R1 would be equal to K, which is constant. The concentration of A for R1 is 0.1. Okay, so 0.1 M, and the concentration of B is 0.1 N. Okay, now R, of course, we saw to be 0.03, so 0.003. That's the value for R1. Now coming here to R3, which is equal to 0.00675. This would be equal to K. The concentration of A for the third reaction is 0.15. So we'd have here 0.15 raised to the power of M and 0.1 for B raised to the power of N. Okay, now take note of the fact that we have K and K, or just to put it simply, we'll take the ratio of R1 to R3. So R1 divided by R3 is going to be equal to K 0.1 M 0.1 N divided by K 0.15 M and 0.1 n. This is equal to 0.003 divided by 0.00675. Okay, now notice that 0.1 n raised to the power of n can cancel 0.1 raised to the power of n that we also have here, and k can also cancel k. Okay, so we're left with 0.1 raised to the power of m divided by 0.15 raised to the power of m, which is equal to 0.003 divided by 0.00675. Okay, now in exponentials, or when we have common exponentials like this, okay, we can simply take the exponential out of the bracket. Take, for instance, you have 2 raised to the power of 2 divided by 4 raised to the power of 2. You could simply take this out of the bracket and it would be 2 divided by 4 all raised to the power of 2, which would be equal to 1 over 2 squared 1 over 4. Okay, and if we also had it this way, we'd have 4 divided by 16, which is also equal to 1 over 4. So for this section, we could simply take the exponent out. So we'd have something like this: 0.1 divided by 0.15. Our exponent out is equal to, now let's take this division. When we divide, when we perform this division, would get about 0.44 to be equal to this. Okay, and 0.1 divided by 0.15 is equal to 0.666. Okay, so 0.666 n m rather is equal to 0.444. Let's move on. Okay, so we stopped at 0.666 n equals 0.444. Now you say, okay, where do we go from here? To move on from here, we'd find the logarithm of both sides. So we'll take the log of 0.666 n equals the log of 0.444. Now, according to the laws of logarithm, if we have log to the base b of a raised to the power of n, it's equal to n log of a to the base b. Applying that here, we would have that n log of 0.666 equals log of 0.444. Okay, now it means that n is equal to the log of 0.444 divided by the log of 0.666. Now this would give us an answer that is approximately equals to 2. So this is m. I've been making use of n. This is m. Okay, m. We're working with m first. So it means that m is equal to 2. And from our reaction here, our rate law here, we can see that m is equal to the order of the reaction with respect to A. So the order of the reaction with respect to A is equal to 2. Okay, now we'll apply this same process for B. Okay, so take reactions X and Y in which the concentration of A changes, but the concentration of B, or rather the concentration of A remains constant while the concentration of B changes. Now taking a look at reaction 1 and 2 that we have here, in reaction 1 and 2, 0.1, 0.15, but for A it remains constant. So we'd make use of reaction 1 and 2. So for reaction 1 and here we have reaction 2. The concentration of B for reaction 1 is 0.1, and for reaction 2 it's 0.15. The concentration of A remains constant at 0.1. Okay, and the order of the reaction with respect to B is N. Okay, now we'll skip all of the processes that we had before and we'll just go directly into R1 divided by R2. Now R1, as we can see here, is 0.03 and R2 is 0.045. Okay, so we have R1 0.003, R2 0.0045. R1 over R2 would be equal to 0.003 divided by 0.0045, and it's equal to K. In the bracket we have the concentration of A raised to the power of M. Okay, although we know it to be 2, would still make use of M. And then the concentration of B, 0.1 raised to the power of N for reaction 1. Then for reaction 2 would have 0.1. The concentration of A remains constant, and the concentration of B is now 0.15 raised to the power of N. Of course, these would all cancel out, and now would be left with this on this side. Now let's do performing this division would have 0.667, and this is equal to, as earlier explained, we could take out the exponent and have 0.1 divided by 0.15 raised to the power of N, and this would be 0.667 equals 0.667. Okay, that's the division, 0.1 divided by 0.15. Now this is very straightforward because we have the same number on both sides. There's an invisible 1 here, so 0.667 raised to the power of 1. Now since the base, which is this 0.667, since the bases are equal, it means that the exponents would also be equal. This is another exponential law, so it means that n is equal to 1. So overall we would have that R is equal to K AM and BN. Now we already got M to be 2, so R is equal to K A square and B raised to the power of 1. Now this simply means that the rate is second order with respect to A and first order with respect to B. However, the overall order of the reaction would be equal to 2 plus 1, which is equal to 3. Having gotten the equation for the reaction rate, we could also calculate the value of K. Now taking or making use of reaction 1, just take up the values of reaction 1, taking the values of R, concentration of A and concentration of B. Okay, so the concentration of A, we have it to be 0.1. The concentration of B, we have it to be 0.1 as well, and the rate of the reaction is equal to 0.003. Now this means that we could substitute all of these values into our equation here and calculate the value of K. So we'll do that very quickly. Making K the subject of the formula, K is equal to R divided by concentration of A square, concentration of B. This means 0.003 divided by the concentration of A, which is 0.1 squared, and the concentration of B is 0.1. This is simply 0.1 cube, so 0.03 divided by 0.1 raised to the power of 3. Okay, so we have K to be equal to 3. Okay, now we could rewrite the rate law as R equals 3 into concentration of A square and concentration of B square. Then you say, what exactly is the unit of K? Okay, what is the unit of K? Now in the next few minutes we'll be taking a look at how the unit of K is derived or ascertained. Now from our example, we had that K is equal to R divided by A squared and concentration of B. Okay, now R is rate. Okay, it's rate, and remember we have here that the rate is equal to the change in concentration of the product, or it could also be the reactant. For the product, we would have a negative sign divided by the change in time. So we have here concentration in moles per liter or per dm cube. 1 liter is equal to 1 dm cube. Okay, so moles per liter, and here we have time in seconds. Okay, so per liter per second. This is the unit for rate. So something like mole per liter per second. Okay, now of course we know the unit for concentration, which is mole per liter. However, the concentration of A is squared, so its unit is also going to be squared. So we'd have mole squared per liter squared. The concentration of B, or overall, let's just take it overall. Overall, we have concentration squared and concentration raised to the power of 1. It means overall we have concentration cubed. Okay, just adding up the exponents 2 plus 3, 2 plus 1 would have 3. Okay, so the concentration of B is in moles per liter as well. Multiplying these two would have moles cubed and moles per liter cube. Now combining all of this together, we would have rate divided by the concentration overall. Okay, so we would have moles per liter per second divided by moles cubed per liter cubed. Now we'll treat each of these individually. So moles here divided by moles, so we have moles divided by mole cube. This would be mole to the -2 power. Okay, rules of exponential rules, it would be 1 minus 3, which is equal to -2. For L, or for liters, would have L minus 1 divided by L minus 3. This would be L minus 1 minus 3. Okay, rules of exponent, when you're dividing, you subtract the exponent. So this is going to become +3 and L is going to become +2. Okay, so now we have moles to the power of -2 liters squared and per second. So there's no second in the denominator, so per second would remain the same. Now this is the unit for K that we derived earlier. This approach can also be used to derive the unit of k for the first order, the second order, and so on. Now, for the zero order reaction, which is R is equal to K, it's very straightforward. Okay, very straightforward. We know rates to be moles per liter per second. So this, of course, would be the unit of K, the rate constant. Okay, now we have seen very briefly the differential equation or the differential rate laws. Let's take a look at the integrated rate law. The integrated rate law tells us what happens to the concentration of the reactant over time. It tells us how the concentration of the reactant depends on time. And it's very interesting because it's actually derived from the differential rate law. Now, the names are not coincidence. We have differential rate law and integrated rate law. Now, it's an integrated rate law because it's actually gotten from the integral of the differential rate law. Now, we have calculus coming to play here. Let's take a look at the zero order reaction. So for the zero order reaction, we had that R is equal to K, because of course the order for the concentration of the reactant is 0, so we just have R equals K. Now, what exactly is R? R has to do with the rate of disappearance of the reactants with respect to time, or the rate of appearance of the product with respect to time. Okay, so let's take, for instance, we have a reaction A reacting to give us the product C. Now, initially we had 5 moles of A. Okay, this was at time 0 seconds. Now, over time, over 2 seconds, we now have 3 moles of C. Now, because matter can neither be created nor destroyed, it means that definitely some moles of A have been converted into C. So that means we now have 2 moles of A and 3 moles of C. Earlier, I stated why this has the negative sign and this has the positive sign. Okay, so final minus initial for the product would be 3 minus 0, which is positive according to the convention. Okay, so divided by the time. Now, as we can see here, rate is, so to say, a derivative. It has to do with change, and derivatives, as we know from calculus, also have to do with change. However, the change being considered here when we have delta A and delta T is an average change. Okay, so it tells you what happens within a time interval. However, we also have an instantaneous change. Okay, now an instantaneous change tells you what happens at an instant in time. Okay, so the instantaneous change would be dA dt. Now, dA dt, unlike delta A, delta T, is not a fraction. dA dt is not a fraction, although it does behave like a fraction. We know this already from calculus, and if we're just getting to know this now, dA dt is not a fraction, although it behaves like a fraction. Now you say, why is dA dt not a fraction? dA dt is not a fraction because dA is not a number and dt is not a number. How are these not numbers? Now we are going into a bit of calculus just for a second. Why is dA dt not a fraction and why is dA not a number? And now dA is a theoretical number. It exists only as a concept, okay? It's not an actual number. And the concept of dA is that dA is a very small infinitesimal value of A. It's so small. It's the smallest number you can think of. Think of the smallest number you know, and the smallest number that is smaller than the smallest number you know. That is an infinitesimal, okay? And you can't exactly say that this particular number is the smallest number that we have on earth. It goes on and on and on and on and on. It's an infinitesimal. It's the opposite of an infinity. Think of the biggest number you know and a bigger number that is bigger than that big number. It goes on that way. So this is not a fraction, but it behaves as a fraction, okay, because we are looking at an instant in time. So dt as well is just a very small time. It gets closer and closer and closer to an instant, just the blink of an eye, okay? Now this is equal to k. The rate is equal to k. Now this is a differential equation, and to solve a differential equation, you take all the variables to one side. You take each of the variables to either side of the equation. So here we have the variable a and we have the variable t. So we'll take a to one side and t to the other side of the equation. So we would have negative dA equals k dt. Now take note of the fact that I said it's not a fraction, but it behaves as a fraction, and that's why we can, so to say, multiply k by dt, okay? Moving on, we have negative dA is equal to kt. Remember, this is for the second, or rather k dt. This is for the first order reaction. Now we want the negative to be on this side, so we'd multiply through by a -1 such that we have dA to be equal to negative k dt. Now we'd simply integrate both sides of the equation. Now integrating, we'll take a definite integral from an initial concentration of A, say A naught, to a final concentration of A dA, and this would be equal to negative k. Because k is a constant, we do not have to integrate it, okay? So negative k dt. We're also taking a definite integral from time t equals 0, so we don't have to include it, but time t naught, t0, and to time t. Now integrating this, you have an integral and you have a differential. It will simply cancel out and you'd be left with a, but of course you're taking a definite integral, and this would be equal to negative k. You have here t, and you're taking a definite integral from t to t naught. Now this simply means that you're going to take a change, so it's going to be a, because of this a, minus the lower limit a naught would be equal to negative k into t minus 0, which is simply t. Okay, so we would have a minus a naught equals negative kt. Now this is the integrated rate law for a zero order reaction. Okay, so a, which is the final amount of the reactant, is equal to the initial amount of the reactant minus the rate constant multiplied by the time. Now taking a look at this equation, we can see that it actually relates the concentration of the reactant to time. Now, very quickly, there's a lot of math here, but we can remember from our general math that we have the general equation, the slope-intercept equation for a straight line, which is y is equal to mx plus c. M here happens to be the slope or the intercept, and c, or rather m here is the slope and c is the intercept. Now, rearranging this equation, we have that AF is equal to negative KT plus A naught. This means that A naught is the intercept, negative K is the slope or the gradient, and T here is simply the variable, okay, the independent variable. So if we have a graph of AF against T, we'd have an intercept at A naught. No, this graph is incorrect. We'd have an intercept at A naught, so this would be A naught. Now, the slope is going this way because it's a negative slope, and this graph here that we had here was incorrect because it would have been a positive slope. A positive slope goes this way and a negative slope goes this way. Okay, now very quickly, let's derive the integrated rate law for a first order reaction. So the rate law for a first order reaction, R is equal to KA. Okay, so we'd apply the same concept, the same idea. So we'd have negative dA dt to be equal to KA. The variables we have A and T, take each of the variables to either side of the equation. Okay, so we'd have negative A divided by the concentration of A, and it's equal to K dt. Now would simply multiply through by -1, so we'd have dA divided by the concentration of A, and this would be equal to negative K dt. All right, now we'd integrate both sides of the equation. So integrating this from a lower limit of A naught to A, okay, of 1 over A dA, and this is equal to K integral dt from t to t naught, which is 0. The initial time is at 0 seconds, and that's why we're making use of 0. Now, this is a very important function in calculus, and you don't have to stress about it. Anytime we're integrating 1 divided by x or y, it simply equals to the natural logarithm of x. Okay, so in this case, we'd have the natural logarithm of A. So ln A from A naught, and this is equal to negative K integral of dt, which is actually t. Okay, but we are taking this from t to 0. Now we're going to substitute. Okay, so this is going to mean ln A minus ln A naught is equal to negative KT. All right, so this means that ln A is equal to ln natural logarithm minus KT. Okay, this is the integrated rate law for a first order reaction, and you could also apply the slope intercept form for a straight line, and see here that the slope is also a negative. Okay, very quickly, let's also derive that for a second order reaction. Now, the differential rate law for a second order reaction is R is equal to K A square. Now, we'd be making use of just A square, but remember that you could also have a second order reaction in this format. Now, making use of this format, we're going to have a more complex derivation, okay? So we'd make use of this format where the reactant is the concentration, the rate of the reaction is only based on the concentration of one reactant. Okay, now same thing applies. The rate is negative dA dt, and this is equal to K A squared. Okay, applying the same rule, take A to one side and take T to the other side. So we would have negative dA concentration of A squared equal to KT. All right, now same rule, have the negative on the K side, is equal to A squared, and is equal to negative KT. Now we'd integrate dk rather, dt, I've been omitting the dt here. Okay, so we'd have integrating both sides from A to A naught, and from, so 1 over A squared dA is equal to the integral of negative K dt from T to 0. Okay, now 1 over A square is equal to A raised to the power of minus 2. And in integrating, when you have when you're integrating, take for instance x raised to the power of n with respect to x, integrating this, what you simply do is you add 1 to the exponent and divide by 1 plus the exponent. Applying that here, we would have this to be equal to A 2 plus 1 divided by minus 2 plus 1, and this is going to give us A to the power of minus 1 divided by minus 1. Okay, so here would have minus 1 over A, okay, minus 1 over A, and we're taking limits from A to A naught, and this is going to be equal to negative KT. Okay, because of course T minus 0 would be T, so we don't have to stress with the limit for this side. Okay, now for this side would have negative 1 over A minus 1 over A naught minus 1 over A naught, okay, because we already have a minus here, minus 1 over A naught, and this is going to be equal to negative KT. Okay, now still using this same page, coming up now, would have negative 1 over A plus 1 over A naught, and this is equal to negative KT. So what we could simply do is rearrange the equation such that we take this to this side and this to this side. Just rearrange it so that the final amount is a positive. So 1 over A, concentration of A, is equal to 1 over A naught plus KT. Okay, this is the integrated rate law for a second order reaction. Okay, this is the integrated rate law for a second order reaction very quickly. And as we can see here, comparing this to the slope intercept form of a straight line, positive slope rather, it has a positive slope or gradient, and so that's why it's going in this direction, unlike the other graphs which would go in this direction because of their negative slope. Alright, so far we have seen that the integrated rate law for a zero order reaction is A is equal to the concentration of A naught minus KT. For a first order reaction, we have seen that the natural logarithm of A is equal to the natural logarithm of A initial minus KT. And lastly, for a second order reaction, we have 1 over A final is equal to 1 over A naught plus KT, the only one with the positive sign, with a positive slope. Let's take a look at half-life. Now, half-life is the amount of time required for half the amount of reactant to be converted into product. Put very simply, so if we have A reacting to give B, the half-life is the time it takes for half of A to be converted into C. This is the half-life. Okay, now we'll take a look at the half-life for a zero order reaction, a first order reaction, and a second order reaction very quickly. Now, starting with the zero order reaction, with the integrated rate law, A equals A naught minus KT. Okay, now A naught is a certain amount of A, but the final amount of A would be half of A naught. The total amount here is A naught, the initial amount you started with, and the final amount would be A naught divided by 2. Okay, so A naught divided by 2 is equal to A naught minus KT. Okay, now we could rearrange this, and this would be that A naught divided by 2 minus A naught is equal to negative KT, such that we have negative A naught divided by 2 is equal to negative KT. So we could simply take out the negative sign, and we would have that A naught over 2 is equal to KT. And since we are finding the half-life, T here, the time, is the half-life. Okay, so the time now is equal to A naught divided by 2K. This time is the half-life for a zero order reaction. It's good for us to take note of this. For the first order reaction, we have ln of A to be equal to ln of A naught minus KT. Okay, and as we earlier explained, A is equal to A naught divided by 2. Okay, the final amount is A naught divided by 2. So here we would have that the ln of A naught divided by 2 minus the ln of A naught is equal to negative KT. Alright, now we know from logarithm that when we have ln of A minus ln of B, this is equal to ln of A divided by B. Alright, so applying that here, we would have ln of A over 2 A naught divided by A naught. Okay, and this is equal to negative KT. Okay, now this is the same as ln of A divided by 2 times 1 over A naught, right? So A naught would cancel out and it's equal to negative KT. So we'll be left with ln of 1 over 2 is equal to negative KT. Do not forget that ln or ln is the natural logarithm, that is log to base e, where e is Euler's number. Okay, now we have this value. Okay, we have this value. Now t, or half-life, which is the time we are calculating here, would be the natural logarithm of 1 over 2 divided by, which is the same thing as times, negative 1 over k. Okay, now we're going to do something very quickly, and very quickly let's take a look at this. Okay, so we have this, we could rewrite this as the half-life. Okay, coming up, the half-life is equal to 1 over k into negative 1 natural logarithm of 1 over 2. Okay, now when we have n ln a, natural logarithm of a, it's the same thing as natural logarithm of a raised to the power of n. Applying that here, we would have t to be equal to 1 over k natural logarithm of 1 over 2 raised to the power of minus 1. Okay, now 1 over 2 raised to the power of minus 1 is equal to 2. So t is equal to natural logarithm of 2 divided by k. This is the half-life for its first order reaction. Okay, first order reaction. The half-life 1 over 1 over t subscript 1 over 2. It's represented in this way. Very quickly, let's take a look at the half-life for a second order reaction. For a second order reaction, we have 1 over a is equal to 1 over a naught plus kt. Okay, now of course a here is equal to a naught divided by 2. So we'd have 1 divided by a naught divided by 2 is equal to 1 over a naught plus kt. Now this is 2 over a naught. Okay, it's the reciprocal. So 1 times 2 over a naught. This is this, okay, and it's equal to 1, or rather minus 1 over a naught is equal to kt. Okay, now we have the same denominator. Okay, so we could simply say 2 minus 1 over a naught is equal to kt. This means that 1 over a naught is equal to kt, and it means that t is equal to 1 divided by a naught k. Okay, this is the half-life for a second order reaction. On taking a look at the half-life for the zero order, first order and second order reaction, we can see that for the zero order reaction, the half-life is directly proportional to the initial concentration. Okay, for the first order reaction, the half-life is independent of the initial concentration, and for the second order reaction, the half-life is inversely related to the initial concentration. Okay, now according to our outline for this video, we have come to the end, but very quickly let's consider the reaction mechanism. Okay, now this is important because the reaction mechanism helps us to understand why we can have two reactants, A and B, and yet the rate law would look something like R equals K A, where B has no effect on the rate of the reaction. Okay, so the concentration of B for a situation like this has no effect on the reaction rate. Okay, and would wonder why. We have two reactants. Shouldn't the concentration of the two reactants both affect the reaction rate? Now this is not always so, and the reason stems from reaction mechanism. Now reaction mechanism breaks down the steps in which a reaction takes place. Okay, so we have the elementary reaction. The elementary reactions are the reactions that make up each step of the reaction. Then we have the overall reaction. The overall reaction looks something like this. It just gives us reactant and product. It doesn't let us in on whether or not there was an intermediate that didn't appear at the end of the result. Okay, now generally in the reaction mechanism we have some steps that are slow and we have some steps that are fast. Now usually the slow step in the reaction mechanism is usually the first step, and the first step is the rate determining step. It's the rate determining step because when the first step is slow, the reaction cannot proceed without completion of the first step. The reaction cannot proceed. It means that the faster the first step, the faster the reaction. In other words, the higher the concentration of reactants you have for the first step, the higher or the faster the reaction overall. A good example of this is, take for example the reaction we have here. Okay, so we're taking a look at the reaction between NO2 and CO2. Okay, this reacts to give, or rather NO2 and CO, this reacts to give CO2. Now this is the overall reaction. However, this reaction has two elementary reactions. Okay, two steps are involved in the reaction. Now the reaction rate as determined experimentally for this reaction is R is equal to K NO2 concentration squared. Okay, so the reaction is a second order reaction with respect to NO2. Okay, now you wonder, why doesn't the concentration of CO affect the reaction? Now looking at the first elementary step of this reaction, okay, the first step of this reaction is that NO2 combines with NO2 to give NO3 and NO. This is the first step of the reaction, and this reaction is slow. Now the second step of the reaction is that NO3 reacts with CO to give NO2 and CO2. Now this reaction is fast. Now notice that the only reactants in the slow step is NO2, meaning that this reaction would either slow down the reaction overall if it proceeds slowly, or it would hasten the reaction if it proceeds faster. Okay, now the only thing affecting whether or not this reaction would proceed fast or slow is the concentration of NO2. Hence, NO2 is the only concentration that affects the reaction overall. Okay, the reaction cannot proceed without the first step. The first step is a slow step, and in order to make the first step fast, the only concentration you need to increase is the concentration of NO2, and that is why at the end CO is not included in the rate law for this reaction. Now, how we derive the overall law for this. So we can see here that NO3 is an intermediate. It's produced in the first step, consumed in the second. This is an example of an intermediate. So NO2 cancels on this side. If we have a species on the product and the reactant side, it cancels out. Okay, when you have A on the product, A on the reactant, it cancels out. So we have NO2 cancelling out. Then we have NO3 rather. Then we have NO2 here on the product side, and we also have it here on the reactant side. It cancels out. Okay, so overall we would have sorry, this is plus NO. Okay, I forgot to include that. Overall we would have that NO2 plus CO2. So we have reactant plus CO would give product, and product, CO2 plus NO. Okay, now we have come to the end of this video on chemical kinetics. If you liked this video, please give it a thumbs up and don't forget to subscribe. Thank you for watching till the end.